Welcome, everyone. I'm excited to kick off our presentation on the history and theory of sets. Today, we'll explore how set theory developed and why it's fundamental to mathematics. We'll cover key historical milestones and the main ideas behind the theory. So let's get started and dive into this fascinating topic. Let's move on to slide 2, where we begin with the definition of sets. A set is simply a collection of distinct objects, which we call elements. These objects can be anything: numbers, letters, or even more abstract concepts. The key idea is that each element is unique within the set. Understanding what a set is forms the foundation for everything else we'll explore today. From here, we'll look into how sets are represented, their properties, and the various operations we can perform on them. This basic understanding is crucial because sets are fundamental to many areas of mathematics, providing a building block for more complex ideas. So, keep in mind, at its core, a set is just a collection of items, but how we work with these collections opens up a whole world of mathematical possibilities. The theory of sets was developed by the German mathematician Georg Cantor, who lived from 1845 to 1918. He actually first came across the concept of sets while working on problems related to trigonometric series. It's fascinating to see how a problem in one area of mathematics can lead to the development of an entirely new branch. Sets have been used in mathematics for a very long time, ever since they were first discovered, and they form the foundation for much of modern math. Understanding sets helps us organize and think about collections of objects in a clear and logical way, which is why they are so central to the field. So, as we explore the origins of set theory, keep in mind how these ideas have shaped the way we approach mathematical problems today. A set is essentially a well-defined collection of objects. When we talk about a set, we're referring to a group of objects that are clearly identified and unambiguous. The objects within a set are called elements, and you'll often hear these terms used interchangeably. For example, if I have a set of numbers like 1, 2, and 3, those numbers are the elements of that set. Sets are usually denoted by capital letters, such as A, B, or C, which makes it easier to refer to them throughout our discussion. The elements within these sets are represented by small letters, like a B or C, which helps us distinguish between the set itself and the objects inside it. Understanding what a set is and how it's symbolized is fundamental because sets form the basis of many concepts in mathematics. They help us organize objects, define relationships, and build more complex ideas. So, grasping these basic definitions sets the stage for everything else we'll explore in this course. Today, I want to talk about the two main ways to represent sets. First, we have the set builder form. This method describes the elements of a set by specifying a property that characterizes all members. It's like saying, the set of all such that is greater than 0. It's very useful when dealing with infinite sets or when a concise description is needed. The second way is the roster or tabular form. Here, we simply list all the elements of a set within curly braces. For example, 2, 4, 6, 8. This approach is straightforward and easy to understand, especially for small sets. Both of these methods are important tools in set theory. The choice of which to use depends on the context and the nature of the set itself. Understanding these representations helps us better analyze and communicate about different collections of objects. Now, let's talk about set builder form. In this approach, all the elements of a set share a single common property that defines them. This property is something that only the elements within the set possess, and anything outside the set does not have this property. For example, consider the set of natural numbers. We can write it in set builder notation as k equals the set of all such that is a natural number. This way, we're specifying a property that characterizes every element in the set. Moving on to the set's representation, there's also the roster or tabular form. Here, we list all the elements explicitly, separated by commas and enclosed within braces. For instance, if we take the set of numbers from 1 to 10, we write it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This method is very straightforward when the set has a manageable number of elements. Understanding these two forms, set builder and roster, is important because they are fundamental ways of describing sets clearly and precisely. They help us communicate exactly which elements belong to a set and under what conditions. This is a key concept in understanding how sets are defined and used within the broader scope of mathematics. Let's take a closer look at some common sets of numbers in mathematics. First, we have Q+, which represents the set of positive rational numbers. These are numbers that can be expressed as a fraction, where both the numerator and denominator are integers, and the denominator is not 0. Next, we see Q, the set of all rational numbers. This includes both positive and negative fractions, as well as 0. Rational numbers are quite versatile because they can be written as ratios of integers. Moving on, the number 5/2 is an example of a positive rational number, highlighting how fractions can be part of these sets. Then, Z plus, or Z plus, refers to the set of positive integers, which are whole numbers greater than 0, like 1, 2, 3, and so on. Now, Z plus also includes the set of positive real numbers, which covers all numbers greater than 0 on the number line, including decimals and irrational numbers, like pi or the square root of 2. The set of all integers, Z, includes positive numbers, negative numbers, and 0, so it's quite comprehensive in that sense. Moving further, R plus, or R plus, is the set of all positive real numbers, encompassing all numbers greater than 0, whether they're rational or irrational. Then, Z is again the set of all integers, which is broader than just the positive integers, since it includes negatives and 0. Finally, R, the set of all real numbers, includes every possible number along the number line: positive, negative, fractions, irrational numbers, and 0. And at the very end, N stands for the natural numbers, typically the counting numbers starting from 1 onward. So, these sets help us organize and understand the different types of numbers we encounter in mathematics, each with its own specific characteristics. Let's delve into some fundamental concepts of set theory that help us understand how sets relate and differ from each other. First, we have the universal set, which includes all the objects we're considering in a particular context. Think of it as the big picture set that contains everything we're working with. Next, we encounter subsets, which are smaller collections entirely contained within a larger set. For example, if our universal set is all fruits, then apples could be a subset of that set. Now, sets can be finite or infinite. Finite sets have a limited number of elements, like the set of days in a week, while infinite sets go on forever, such as the set of all natural numbers. Recognizing whether a set is finite or infinite helps us understand its structure and complexity. Moving on, the power set of a set is the collection of all possible subsets of that set. So, if we have a set with 3 elements, its power set will include the empty set, the individual elements, and all combinations of those elements. Another important concept is equal sets, which are 2 sets that contain exactly the same elements, regardless of how they are described or written. We also have the empty set, sometimes called the null set, which contains no elements at all. It's a fundamental building block in set theory. Finally, these concepts help us understand the different types of sets we encounter. They form the foundation for exploring more complex relationships and properties within set theory, which is essential for building a solid mathematical framework. All right, let's talk about the empty set, which is a fundamental concept in set theory. A set that contains no elements at all is called the empty set, or sometimes the null set or void set. We often denote it using the symbol letter 3D5 or simply with curly braces, with nothing inside. For example, consider the set R defined as x, 1x2, is a natural number. Since there are no natural numbers between 1 and 2, this set is empty. Understanding the empty set is crucial because it acts as the building block for other sets. It's like the foundation in a structure, important for understanding how sets relate to each other and how to perform operations like union and intersection. So, in the broader context of set theory, recognizing and working with the empty set helps us develop a clearer understanding of the properties and behaviors of sets in general. Let's talk about sets now. When we say a set is finite, we mean it either has no elements at all or it has a specific, countable number of elements. For example, think about the set of days in a week. That set is finite because it has exactly 7 elements. On the other hand, if we consider the set of all points on a line, that set is infinite because there are endlessly many points. No matter how closely you look, there's always another point in between. Recognizing whether a set is finite or infinite helps us understand its structure and how we can work with it in various mathematical contexts. This distinction is a fundamental concept that ties into the broader themes of set theory and understanding the nature of different collections of objects. Let's talk about when two sets are considered equal. So, given two sets, K and R, we say they are equal if they have exactly the same elements. That means every element in K must be in R, and every element in R must be in K if that's the case. We write K equals R, or K equals R on the other hand, if they don't have the same elements. Maybe one has something the other doesn't. They are considered unequal, and we write K not equal to R, for example. If we have K equals 1, 2, 3, 4, and R equals 1, 2, 3, 4, then we know K equals R because they contain exactly the same elements. This concept is fundamental because it helps us understand when two sets are truly the same, even if they might be written differently or in a different order. Remember, the key point is that the elements must match exactly for the sets to be equal. A set R is said to be a subset of a set K if every element of R is also an element of K, in other words. Rk means that all the elements contained in R are also contained in K. This concept of subsets is fundamental because it helps us understand how sets relate to each other, especially when we want to compare their contents. It's a way of showing that one set is entirely included within another, which is crucial for building more complex ideas in set theory. Remember, recognizing subsets allows us to organize and classify sets based on their elements, tying directly into the broader themes of structure and relationships in mathematics. Let's talk about the power set of a set. The set of all subsets of a given set is called the power set of that set. Now, when we refer to the power set of a set, we usually denote it by P of that set, so P. K. If our original set is K, an important thing to remember is that every element within the power set is itself a set. For example, if our set K is 1, 2, then the power set Pk includes the empty set, which we write as phi, the singleton sets 1 and 2, and also the set containing both elements, which is 1, 2. This concept is fundamental because it helps us understand how subsets relate to the original set and how we can work with collections of sets in a structured way. As we move forward, keep in mind that the power set provides a comprehensive way to look at all possible combinations within a set, which is a key idea in set theory and its applications. Let's talk about the universal set. The universal set is essentially the set that contains all objects we're considering in a particular context. An interesting thing about it is that it includes itself. Yes, it's a set that contains everything, including itself. For example, if we think about the set of all real numbers, that set would be the universal set for all other sets of numbers. However, there's an important note to keep in mind. In some cases, like when dealing with roots, we exclude negative roots from the universal set. This helps us avoid certain paradoxes or contradictions. Understanding the universal set helps us see the bigger picture in set theory, because it acts as the foundation or the everything set from which all other sets are derived. It ties into the overall theme of how sets relate to each other and how we define the boundaries of our mathematical universe. Let's take a closer look at the sets of rational numbers, integers, and natural numbers. First, the set of rational numbers, which we denote as Q, includes all numbers that can be expressed as a fraction p over q, where both p and q are integers, and q is not 0. An important point here is that the members of Q also include negative numbers, so it covers all fractions and their negatives. Next, we have the set of integers Z, which includes all whole numbers, both positive and negative, as well as 0. Think of it as -2, -1, 0, 1, 2, 3. This set is fundamental because it forms the basis for many other number systems. Finally, the set of natural numbers, n, consists of all positive counting numbers starting from 1, so 1, 2, 3, and so on, extending infinitely. Sometimes people include 0 in natural numbers, but in this context, we're starting from 1. Connecting these points to the overall theme, understanding these basic sets helps us grasp how different types of numbers relate to each other and form the building blocks of more complex mathematical concepts. Each set has its own unique properties and plays a vital role in various areas of mathematics. Let's take a closer look at the concept of intervals in the set of real numbers. When we write a, b, we're talking about what's called a closed interval. This means that it includes all the points between a and b, and importantly, it also includes the endpoints a and b themselves. So, if you think about the interval from 1 to 5, it contains every number starting at 1, going up to 5, including those two boundary points. Now, on the other hand, when we write a b, we're dealing with an open interval. This includes all the points between a and b, but excludes the endpoints. So, in the case of an interval from 1 to 5, it contains all the numbers greater than 1 and less than 5, but not 1 itself, nor 5. Understanding these distinctions is crucial because they tell us how the interval behaves at its boundaries, which can affect limits, continuity, and other properties in analysis. Overall, recognizing whether an interval is open or closed helps us precisely describe subsets of real numbers and their properties in our broader exploration of real analysis. All right, let's talk about the different types of intervals. When we're working with intervals, the key thing to remember is whether the endpoints are included or not. For example, a x less or equal to b means is greater than a but less than or equal to b. Notice how the less than or equal to sign includes the endpoint b, so b is part of the interval. Then we have a b, which is similar but the start point is not included, so it's open at a, but the endpoint b is included. This is often called a half-open or half-closed interval. Moving on, a less or equal to b means is at least a but less than b here, a is included, but b is not. This kind of interval is also half-open, but in the opposite direction. Finally, when you see a, b, both endpoints are included, so can be equal to a or b and everything in between. And conversely, a b means is strictly between a and b, excluding both endpoints. Understanding these differences is crucial because they affect how we include or exclude boundary values in our analysis, and that ties directly into how we interpret real-world data and functions. So, recognizing whether an interval is open, closed, or half-open helps us define the precise set of values we're dealing with in any problem. Venn diagrams typically consist of rectangles and closed curves, usually circles. The universal set is usually represented by a rectangle, while its subsets are shown as circles inside it. These diagrams are a visual way to illustrate the relationships between different sets. A Venn diagram, or set diagram, helps us understand all the possible logical relations among a finite collection of sets. Interestingly, they were conceived around 1880 by John Venn, which is where they get their name. Today, we use Venn diagrams not only in elementary set theory, but also across various fields like probability, logic, statistics, linguistics, and computer science. They're a powerful tool for visualizing complex relationships in a simple, intuitive way. In this slide, we're looking at some set notation and relationships within a universal set, which here is represented as U equals the numbers from 1 to 10. So, think of U as the entire universe of our discussion. We have two subsets, A, which includes the numbers 2, 4, 6, 8, and 10, and B, which is just 4 and 6. Notice that B is a subset of A, meaning all elements of B are also in A. This is highlighted by the notation B is a subset of A, or BA. Now, moving to the illustration, we see that the universal set U remains the same, but A is slightly different. Instead of only those specific elements, A here includes 2, 4, 3, and the rest up to 10, which shows that it can be a larger set containing various elements from the universe. The key point to take away is understanding how subsets relate to the universal set and to each other. The notation B emphasizes the subset relationship, where B is completely contained within A. Recognizing these relationships helps us grasp how sets interact within a larger context, which is fundamental to understanding set theory and its applications in problem solving. Now let's talk about the union of sets. The union of two sets, A and B, is essentially a new set, which we call C. This set C contains all the elements that are in A, in B, or in both. Think of it as combining everything from both sets into one big collection. If you look at the diagram, you'll notice the purple part, which visually shows us the union, or what we call a cup B. It's a helpful way to see how these sets come together. Understanding the union is key, because it helps us see how different groups or collections overlap and combine, which is a fundamental concept in set operations and in broader problem solving. So remember, the union is about bringing together all elements from both sets without duplication, creating a comprehensive set that includes everything from both sides. Let's take a closer look at some key properties of the union operation. First, we have the law of the identity element, which states that a union with the empty set letter 3D5 equals A essentially. This means that adding nothing to it doesn't change at all. Next, there's the law of U, meaning that the union of the universal set U with any set A still results in U, because U contains all elements. Moving on, the associative law tells us that whether we unite A with B first and then with C, or unite B with C first and then with A, the result remains the same. This property is crucial because it allows us to regroup unions without changing the outcome. The idempotent law states that a union with itself is just A, so combining a set with itself doesn't add anything new. And finally, the commutative law indicates that a union B is the same as B union A. The order in which we union sets doesn't matter. These properties are foundational because they help us understand how union behaves logically and mathematically, tying into the broader theme of set operations and their characteristics. Let's take a closer look at some properties of the intersection operation. First, notice that the intersection of the empty set with any set, such as letter 3D5A, is always. This makes sense because there's nothing in the empty set to intersect with A similarly. The intersection of the universal set U with any set A is just O itself, since U contains everything, so intersecting it with A leaves A unchanged. These are known as the laws of letter 3D5 and U, and they set the foundation for understanding how intersection behaves with special sets. Next, consider the distributive law. A BC equals a B, a C. This property is quite useful because it allows us to break down complex intersections involving unions into simpler parts. It's like distributing A across the union, which helps simplify many set expressions. Then there's the idempotent law. A equals A. This might seem obvious, but it's important because it confirms that intersecting a set with itself doesn't change it. It's a fundamental property that helps us understand the stability of sets under intersection. The associative law states that a BC equals a BC. This property shows that the grouping of intersections doesn't affect the result. So, whether we intersect A with B first and then with C, or B with C first and then with A, the outcome remains the same. This is very handy when working with multiple sets. Finally, the commutative law tells us that a B equals BA. In other words, the order of sets in an intersection doesn't matter. Recognizing this helps us manipulate and simplify set expressions more flexibly. Overall, these properties highlight the consistent and predictable behavior of the intersection operation, which is essential for understanding how sets interact in more complex scenarios. Let's consider a simple example to understand the concept of a complement of a set. Suppose we have the set U equals 1, 2, 3. Now, imagine we have some subset A within this universe. The key idea here is to look at all the elements in U that are not in A. These elements form what we call the complement of A, which we denote as A. It's important to note that the complement depends on the universe we're considering. In this case, our set USO, A includes everything in U that doesn't belong to A. This concept is fundamental because it helps us understand what is excluded from a set, and it plays a crucial role in set theory operations. By defining A this way, we gain a powerful tool to analyze relationships between sets, especially when we're interested in what is outside a particular set within a given universe. This idea of complements is essential as we explore more complex set operations and their applications throughout the presentation. Let's take a closer look at some fundamental properties of complements of sets. First, we have the laws involving the empty set and the universal set. Notice that the complement of the universal set U is the empty set lek thruduf of, and vice versa. The complement of lek thruduf of is U. This makes sense because the universal set contains everything, so everything outside it is nothing, and outside the empty set, everything is in the universe. Next, we see De Morgan's laws, which are crucial because they relate the complement of unions and intersections. Specifically, the complement of a union B equals the intersection of the complements of A and B. Similarly, the complement of a intersect B equals the union of their complements. These laws help us simplify and manipulate set expressions, especially when dealing with complex combinations. Another key point is the law of double complementation, which states that taking the complement twice brings us back to the original set. So, the complement of A is just A again. This concept reinforces that complements are involutive operations. Finally, we have the complement laws related to A and its complement A. The intersection of A and A is the empty set because they are disjoint. Meanwhile, their union is the universal set, since together they cover everything within our universe. All these properties are interconnected, and understanding them helps us work more effectively with set operations, especially in areas like logic, probability, and computer science. They form the backbone of how we reason about sets and their relationships. And that wraps up our discussion on the history and theory of sets. Thank you for your attention and engagement throughout this journey. I hope you now have a clearer understanding of how sets have evolved and their fundamental role in mathematics. Remember, these concepts form the foundation for many areas we'll explore further, so keeping them in mind will be very beneficial. If you have any questions or want to delve deeper, feel free to reach out. Thanks again for your participation, and I look forward to our next discussion.